Hello and welcome to iitiansgateclasses once again. And we are starting with the optimal merge pattern. So this is also a greedy algorithm only. So let me define the problem first. That suppose that we are given with n number of files. Each file contains some records. Okay, each file contains some records. And what do we need to do is we have to merge these files into a single file by doing merging will be done by taking two files, okay, at a time. So merge files into a single file such that we can take two files at a time. Yeah, sorry for that. So we need to merge file into a single file, and we can merge two files at a time. So the cost of merging will be number of records for each file have. For example, if we are merging a file F1 with 50 records, F2 with 180 records. So the cost of merging these two files into one file 1 have 50 records, okay, and file 2 have 180 records. So cost of merging these two files into a single file will be the summation of these two, which is 230. 230 is the cost of merging. Okay, I hope you get the problem now. So if we are given with n number of files and we have to merge all these files into a single file, each file contains some record, and at a time we can pick only two files to merge, right? So if we merge these two files, we will have some F3 with 230 records, and cost is also 230. For this merge operation, we have taken a cost of 230. So now the solution of this problem is same as Hoffman encoding. Okay, you need to build a min heap where the minimum element is at the top of the heap, is at the root. You will delete that element and try to merge it with the second minimum. Once you delete the minimum element, the second minimum will appear at the top after deletion operation. You will delete that and merge that one. Okay, so that will be our first operation. So once you merge these two files, the minimum two files, what will happen that you will have a file, the third file, and you will need to insert this file into min heap. Okay, let's start with some example. Okay, so for example, if you are given with three files like F1 equal to 50 records, F2 equal to 180 records, and F3 equal to 70 records. Now, how can you do it? You can do it in several ways, but what is the best way? Let's do it in a very non-intuitive way. Let's start with some operation. For example, if we have F1 equal to 50, F2 equal to 180. First, we are saying that, okay, let's merge these two and have some F4 with 230 records. Okay. Now, these two are already merged, right? And we have only two files, F4 and F3. So we will merge F4 and F3 also. Once you merge, we will have a file of F5. This is the last file with 300 records. So now all the records are in a single file. And what is the total cost? So we have done two merge operations. First merge operation we have done here. We have done exactly two merge operations. The first merge operation we have done here. Okay. And the second merge operation we have done here. What is the total cost of this merge operation? Cost is 230. This merge operation cost is 300. Okay. So the total cost is 230 plus 300, which is equal to 530. So the total cost to merge all these files into one is 530. Can it be reduced? Let's see one more, like one more tree. Let's construct one more tree and try to bring down this cost. How can we bring down? We are saying that first we will be picking the minimum cost. So we are given F1 with the 50 records, F2 with 180, F3 with 70 records. Okay, with 70. Let's construct a tree again. Okay. So we have built a min heap. If you try to build a min heap using these, so the min heap would look like this. 50. Either it will look like this, 70, 180, or it will look like this, 50, 180, and 70. Out of these two. So this is the min heap. Okay, min heap. Once you construct the min heap using these three files, you will have these, either this min heap or this min heap. Okay, now our algorithm says that first have minimum two. Like the first one is this. Once you delete 50 from here, this min heap will look like this, 70 and 180. Okay. After deletion operation, we put the last element at the top and then we try to balance the tree again, right? So after balancing, our tree would look like this. So you say that, okay, I have picked this F1 with 50 records. Now again, using this min heap, I have a second minimum file, F3 with 70 records. So I will merge these two first. So using this, you will delete 70 again. So you have 180 only. So this is the remaining min heap. After deletion, two minimum records. So let's merge these two. So once you merge, you will have a file F4, which contains total records of 120 only. 120, right? What is the cost here? Let me write the cost in. Cost of this merge operation. Cost equal to 120. So it have a cost of 120. Now you put this 120 back in the min heap. You put this 120 back in the min heap. You try to insert 120 here. Okay. And try to balance it again. Our resultant min heap will look like okay. Let me try to first construct a min heap and do it operation by operation so that you know how min heap works. You already know, but it will be better for you to understand. If we are saying that our min heap is looking like, let me construct min heap using blue. Initially, our min heap will look like this: 50, 70, and 180. Once we delete this minimum element and try to put it here, our min heap will look like this: 70 and 180. After doing all the operation, balancing and all those things, okay, which I explained earlier, our min heap will look like this. Now you want the second minimum also. So you delete 70, or min heap will look like this, 180. Okay, so this is our resultant min heap. Once you do the merging, after merging, whatever result you have, you will put that also into the tree. Okay, so once you insert 120, our min heap will look like this: 120, 180. Okay. Now you delete two elements and try to do the insertion. Try to do the merging. So the first one is this one. We already have this one here. You delete this one. Then you delete 180. F2 equal to 180. Okay, and you merge these two. You merge these two. So the F5 contains 300 records at last, and our cost here is, our cost of this merging is 300. So what is the total cost? Now it's 300 plus 120, which is 420. Previously our cost was 530, which reduced to 420 only. So this is how you will construct a tree-like structure, and this is optimal merging or optimal merge pattern. Okay. So let's take more complex example where we have 7 files given, like a file A have 9 records, B have 13 records, C have 23 records, okay, D have 29 records, E have 15, F have 10 records, G have 14 records. Okay. So let's try to build the merging here and min heap here. Okay. Let's build a min heap here. Okay. So how can you build a min heap? You will build min heap something like this. Okay. First you insert all the elements in the order. Then you do the shuffling. 29, 15, 10, and 14. You will start from the bottom. Then we will start from the bottom. Here we do the shuffling first. After shuffling, let me use green color. You know that 10 is the minimum. It will come here, and 23 will come here. Here 13 is the minimum, which is already present here, so no issue. Here 9 is the minimum, so there is no issue. So resultant min heap will look like this only. After improvements, our resultant min heap will look like 10, 23, and 14. Okay. It will look like 10, 23, and 14. Okay, so this is our min heap. Okay, so this is A, this is B, this is 10 is F, and here this 29 is D, 15 is E, 23 is C, and 14 is G. Okay, so let's construct our optimal merge pattern. We need to merge all these files into one by taking 2 files at a time. Okay, so how can we build it? First, have two minimum element. After deletion of 9, it says that, okay, let's merge A equal to 9 here. And the second minimum is F. I'm not doing the balancing again and again, right? So after deletion to the minimum 2, F equal to 10. And once we merge, let's consider some notation like A1 here, which indicates that this is the intermediate file. This is not from the beginning, and this is intermediate file which we created after merging. It contains 19 records. Okay. So after deletion of these two, after deletion of 9, a tree would look like this. Okay. Our tree would look like this: 10, 13, here 29, 15, and here it will look like 14 and 23. Once we delete the 10 also, our tree will look like this: 13 and 13 will come here, and it will try to, we put 23 here, then it will be shuffled with 13, and 23 will be shuffled with 15. So it will be 15, 14, 29, and 23. After deletion and balancing, or doing all the operation of balancing or all such things, our tree will look like this. Okay. So this is 19. Now we need to push the 19 here. So once we push the 19 here, so this is the right position of 19. There is no shuffling required, right? In min heap. This is min heap. Condition is the parent at each node should be less than the children. Okay, so 19 is greater than 14, so there is no issue. 14 is less than 19. So we need to delete again the minimum 2, right? Again, we need to delete the minimum 2. So the minimum 2 is 13. So this is A1. 13 is what? B. B equal to 13. Right? So here the minimum are B equal to 13 and 14. 14 is G. So G equal to 14. We need to merge these two. 19 is the node. 19 is not the minimum out of all these files, including the intermediate file. So first, the merging of these two will happen. Okay, merging of these two will happen. So let me try to write it in a better way. 13 and 14. Here it is like B equal to 13 and G equal to 14. Merging of these two will happen. And we create an intermediate file A2 after merging. And how many operation will it take? It will take 27 merging. The cost is 20. We will calculate cost later on. First, let's construct the optimal merge pattern tree. So after deletion, I have to write the min heap in the next page, right? So after deletion of 13 and 14, our tree will look like, let's delete 13 first, okay? And let's see how our tree will look like. So right now our tree is 13, 15, 14, 29, 23, and this is 19 here. Okay, let's delete 13. After deletion of 13, the last element will go here and balancing will happen. Once 19 will go here, it will be balanced out by the minimum element, which is 14. So 14 will be replaced by 19. It will look like 14, 15, 19, 29, and 23. This is our resultant tree. Once we delete 14, the last element, which is 23, will take place here. Okay, and the balancing will happen. So after balancing, it will look like something like 15 will be replaced by, so 23 will be replaced by 15. So it is 15, 23, 19, and 29. So this is our resultant tree. Okay. So now we have a new node, 27, which will be added at the last position, 27, A2. As you can see right now, it is at the last position. You don't have to do anything at all. Okay, because it's already greater than its parent. So we don't have to do any shuffling. So this is our resultant min heap. Okay. So what is our minimum right now? 15 and 19. What is 15? Like if you see here, 15 is E, and 19 is A1. So we will merge these two. E equal to 15, and we'll merge these two. Okay. And again, we will rebalance this min heap. Once we merge, we will have A3, which will have how many files? 15 plus 19. Okay, 30 and 34. It will have 34 files, right? Yeah. A3, 34. Let me confirm this that we are going in right direction. We need to insert 34 there, right? So F is 10, A and F. Yeah, so this is correct. So we will have 34 here, 34 in A3. We need to insert the 34 and delete these two. First, we will delete A1 and E from this tree. Once we delete this one, 19 will take place here, right? So first this will go there, right? Okay, let me try to write them once again. 15, 23, 19, 29, and sorry, 29 and 23. Okay, this is not 23, it's 27. This is A2, 27. 27. Okay, once we delete this, 27 will go here and rebalancing will happen. After rebalancing, 19 will come here. Okay, so it will look like 19, 23, and 27, 29. Okay, 27 will go there on the top. And balancing will happen. Once we delete 19, the last element 29 will go here and the balancing will happen. 29 will be replaced by 23. So it will be 23, 29, and 27. So now we need to insert A3 34 here, 34, which is already less than greater than its parent. We don't have to do anything. So this is our resultant mean heap for now. Now this 23 is what? 23 is C. Okay, and 27 is what? These two are the least minimum right now. Okay, 27 is A2. A2. So we will merge C and A2 into one. Okay, so we will delete these two first. Once we delete these two, our tree will look like this 29 and 34. Okay, this is our resultant mean heap after deletion of C and A2. So let's merge C and A2. If we merge C and A2 here, C equal to 23. Okay, let's merge these two. Once we merge, we have a file A4 containing how many records? Let me erase this intermediate mean heap. If you already noted down this, if you haven't noted down this, you can go back and check the intermediate mean heap. Intermediate mean heap is not required. It's just for your understanding, like how mean heap works. Okay, once you merge these two, A4 will be created and it will have 50 records. Okay, so we need to insert 50 also here. So we will insert 50 in the mean heap. Right, what we are doing, using mean heap, we are identifying the minimum two files. Okay, files which contains minimum number of records. Those minimum two files we are discovering and we are merging into one. So the resultant file, whichever is created after merging, will be again inserted into mean heap. Okay, so these are the operation you need to do. Then again the minimum file, minimum two will be pulled out. Now if you see here, we have 29, 34, 29. So 29 is D basically. 29 and 34. So once you merge D equal to 29 and 34 into one, A5 will be created, right? And it will be 63, I think, 63, yeah. Now we have only two files, A4 and A5. These two will be merged. And we have a file A6, which is 113. So what is the cost here? What is the total cost here? Total cost you can count also yourself. That this is one merging. Okay, this is one merging. This is one merging. So this is one. This is two. I'm just counting the merging, and you can add the map. You will get the minimum cost. Let me go in the order in which we did this. First, we did this merging. Okay. Then we did this merging. Then we did this merging. So this will be 3. Then we did this merging. This will be 4. Then we did this merging. This will be 5. And this will be 6. So we have 6 merging in total. Let me write down this tree again with better edges and nodes. So we have 113 at the top, 63, 50 here, 63, 50 here, right? And 34, 29, 34, 29, 23, 27, or 27, 23. I can write it like this. (27) and 23 and 34. You can say that it's E. I can write 15 here, and here I have 19, 9 and 10. 19, 9 and 10. 27 is 13 and 14. 13 and 14. So this is our tree. I think that's it. 27, 1, 2. Yeah. This is our tree. So we can calculate cost here. So the internal nodes are cost basically. The internal nodes are cost. You can assume that once you construct this tree, the internal node are cost. You can sum up the internal node cost. Okay, because the operations are happening like this is happening first, then this is happening second. Okay, this is our third operation we did. This is our fourth operation. This is fifth operation, and this is our sixth operation. So the cost is 19. First operation 19, second operation 27, third operation is 34. You just have to add internal nodes. Okay, 34 plus 50, fourth operation. Fifth operation is 63, and this one is 113. If you add all these up, we can have the minimum cost of merging all the trees, all the files, right? If you don't construct mean heap, it's okay. What you can do, you can merge 2 files, create the intermediate file. Out of the remaining and intermediate file, you can identify minimum 2 files. Okay, and again add that up. So without minimum tree, without mean heap, I again create this. I again do this example. A equal to 9, B equal to 13, C equal to 23, D equal to 29. E equal to 15, F equal to 10, G equal to 14. If somebody asks you that using a mean heap, I am doing this because that is the optimal way if you use mean heap, right? But if somebody don't ask you what is the structure of mean heap after 4th step or 5th step, you don't have to construct the mean heap. Okay, you don't construct the mean heap. That will take more of your time. Okay, so let's construct the tree. Initially, we have these 2 minimum, 9 and 10. So we'll say that, okay, 9 and 10. This is 19. You put 19 here and delete these 2. So what is the current minimum including this 19? 13 and 14. So 13 and 14. These 2 are the, like you can see here, 13 and 14. So this will make 27. Okay, so you put 27 here and delete these 2. What is the minimum 2 right now? This 19 and 15. This 19 and 15. Okay, so this will sum up to, so 19 and 15 sum up to 34. You put 34 here. Now what is the minimum 2? 27 and 23. 23 here. You will merge these 2, 50 will come and you will append 50. Now in the remaining one, what is the minimum 2? 34 and 29. So put 29 here, and this will be 63. Now only two are remaining, 50 and 63. So this is 113. So this is the easiest way. And now all the internal load, if you sum up all the internal load, it will give you the minimum for optimal merge pattern, the minimum cost for the optimal merge pattern, right? So you just have to add all the internal nodes. This is one internal node. This is leave the leaf nodes, right? So it is 113 plus 63 plus 50 plus 34 plus 27, 1, 2, 3, 4, 5, one more plus 19. Okay, this is our cost, minimum cost to merge n number of files into a single file. So that's it for the optimal merge pattern. And what is the time complexity for this one? If we are considering min heap, how many operations are we doing? For each pair of files, you are doing 2 deletion and 1 insertion, right? For each pair of files, you are doing 2 deletion, 1 insertion. Initially, build heap will be called build heap, which will take order of n. If we have n number of files, n files, build heap will be called, which will take order of n. Then we will do n number of around n number, not exactly n, it could be n minus 1, n number of n number of times we will do 2 deletion. Okay, for each merging, first we identify 2 minimum and we merge them into 1. And again, the merged file will be inserted into the min heap. So 1 insertion. Okay, this will take 3 log n time, 3 log n. Okay, if you are doing n number of time, this will be 3n log n, okay, which is equal to order of, if you sum these up, like n, order of n plus order of 3n log n, it will be equal to order of n log n. So this is our time complexity for optimal merge pattern, order of n log n. Okay, so now let's move on to the next topic now, which is minimum cost spanning tree. First, before going to minimum cost spanning tree, first you need to understand what is a graph, what is a simple graph. So because we build minimum cost spanning tree on a simple graph. Okay. In the simple graph, between there are very basic logic. That first condition is no parallel edges are allowed. Second thing is self loop not allowed. Self loop is not allowed. For example, if you have nodes like this, you can't do this. This is not allowed. You can't do, if you have one edge between these 2 nodes, a undirected edge between these 2 nodes, you can't do one more edge undirected. Okay, undirected means if the direction is given like this, then this can happen. But we are considering simple graph for undirected graphs only. There is no direction given. In min heap, there is no, in minimum cost spanning tree, there is no direction. It's undirected. Okay. In undirected, you cannot have loops like this, or you cannot have parallel edges. Okay. It will simply look like this. These are nodes, these are edges. Okay. The edges represent the connection between these 2 nodes. Okay. So there is one simple graph and there is one multi-graph. In multi-graph, we can have multiple edges like this, multiple edges, infinite number of edges. Okay, between each pair of nodes, you can have infinite number of edges in multi-graph. So for spanning tree, we are considering simple graph. In simple graph, for each pair of nodes, we can only have one edge. That's it. And weight on that edge will be given. Now, let's consider types of simple graph. Types of simple graph. First one is null graph. Null graph. Okay. In null graph, there are no edges. Only nodes are present. There are no edges. Only nodes are there. Something like 1, 2, 3. So these are the nodes, but there is no edge. Okay. So 0 edges. 0 edges. If there is no edge, it's called null graph. Then there is one type called complete graph, where we have all the edges. For example, 1, 2, 3, 4. So we have all the edges. 1 to 4, 1 to 2, 1 to 3. Similarly, this is 1 to 2 to 1, 2 to 4, 2 to 3, and 3 to 4. So we have all the edges. We have all edges. Okay. So a complete graph with 4 nodes is called K4. It represented as K4. Complete graph with 4 nodes. Complete graph with 3 nodes represented as K3. K3 will look like this. Okay, this is K3. Okay. So in complete graph, number of edges would be are maximum in a complete graph with respect to simple graph we are saying, okay, which is equal to n minus 1 by 2. N is equal to number of vertices we have. Vertices or nodes, okay, vertices or nodes. So if we have n nodes or n vertices, in case of complete graph, we have total how many edges? N minus 1 by 2. So let's consider a graph with 4 nodes. Okay. How many edges do we have maximum in a complete graph? Complete graph have maximum edges, right? So how many edges can we have? For 4 nodes, we have 1, 2, 3, 4, 5, and 6. Okay, we have 6. N equal to 4 here. So if we use this formula, it will be 4 multiplied by 3 divided by 2, which is 6. Okay. So how many simple graphs are possible for n number of nodes? For example, if you have n equal to 2 nodes, number of simple graph how many simple graphs are possible? Sometimes these kind of question can be asked in very simple optional way or numerical way, that calculate number of simple graphs for given number of nodes. For if you have 2 nodes, we can only have 2 graphs. Like one is null graph, another one is complete graph. There is no incomplete graph in case of 2 nodes. Let's consider n equal to 3. So number of graphs are 2. Number of simple graph are 2. If we have 3 nodes, right? So let's construct all the graphs. 1, 2, 3. One is this one. Second one is 1, 2, 3. Third one is 1. This is third. Okay, then we have 1, 2, 3. This is our fourth graph. Then we have 1, 2, 3, like this. 1, 2, 3, like this. Okay. Then we have 1, 2, and 3. 1, 2, 3, 4, 5, 6. We can also have 1 to 2. 1 to 2 we already considered. 1 to 3 we already considered. 2 to 3 we already considered. So 1 to 2, 1 to 3, 1 to 2. Okay. Then we can have something like this. And the last one is complete graph. Okay. So we have total. When n equal to 3, number of simple graphs are 8. So if somebody tell you that n equal to 15, what are the number of simple graphs? So there must be some formula, right? You cannot construct for n equal to 15, you cannot construct all these graphs like you have constructed for n equal to 2, n equal to 3, or n equal to 2, right? So the formula is very simple. It's like number of simple graphs equal to 2 to the power maximum number of edges possible. How many maximum edges are possible? 2 to the power n minus 1 by 2. So this is the formula. For example, let's consider n equal to 3. We know that we already calculated number of simple graph are 8. Okay, 8. So 2 to the power 3 minus 1 divided by 2, which is equal to 2 to the power 3 multiplied by 2 by 2, which is 2 to the power 3, and 2 to the power 3 is 8. So the formula is 2 to the power n minus 1 by 2. These are the number of possible simple graphs. Okay, if you have n nodes given, number of possible simple graphs are these. Okay, remember this. Now there is one more concept, which is, let's see that if number of edges are represented by E, number of vertices or nodes are represented by V. What is the relation between E and V? In worst case, or you can say complete graph, we already know that number of edges are equal to, will always be less than equal to V minus 1 divided by 2. Okay, number of edges are equal to, we have already seen that, right? Here we have seen that. Okay, number of edges are maximum in a complete graph, which is equal to n minus 1 by 2, where n is number of nodes. Okay, here we are saying that let's represent that n with V less than equal to. So let's consider the equal to case where E equal to V minus 1 divided by 2. Okay. Now we want to establish a relationship between E and V. So E is basically equal to order of V square. How come? We can write this down as E equal to V square minus V divided by 2. So using this relation, we can say that E equal to order of V square. Okay, in case of complete graph or worst case, E equal to order of V square. Okay, remember this. Now, what else we can say? If we take log both sides, it will see log of E equal to order of log of V square. No, so the 2 can come here. So it is order of 2 log V, which is equal to order of log V. See the relation? Now E equal to order of V square, but log of E equal to order of log of V. Once we take the log, constant power doesn't matter. Constant power doesn't matter. Log of E equal to order of log of V. Okay, this is very important. E equal to order of V square. And these are the two relationship between number of edges and number of vertices. You need to remember these two relationships. These are very important. Now let's move on to our minimum spanning tree or spanning tree. First, we identify what is a spanning tree. Then first we define what is a spanning tree. Then we move on to minimum spanning tree. Spanning tree. Okay. It is a subgraph. Sorry, not sub, it's sub. It is a subgraph of a given graph G such that this subgraph, for example, this subgraph is represented by S, contains all the vertices or nodes. Second thing is S don't or doesn't have any cycle. Okay, don't have any cycle. I'll tell you what a cycle is. Third thing is S should contain V minus 1 edges only. Okay. Once in a graph, there is no cycle, that can be called a tree. Okay. But in spanning tree, we have exactly V minus 1 edges. For example, if we are given with a graph G, which look like this 1, 2, 3, 4. Okay. So this is a spanning tree. S 1, 2, 3, and 4. How many nodes do we have? N equal to 4. How many edges do we have? 3 only. So you see, should contain V minus 1 edges. But is it a spanning tree? Here also we have 3 edges. But here we have a cycle. From 1 you can go to 4 and then 3, then again you can reach to 1. If you start to 1, you should never come to 1 in a spanning tree. You can never come to 1 again. Here, if you see that from 1 you can go to 2. Okay. You cannot come, if we are considering only one direction, then I'm saying from 2 you cannot reach 4. From 1 you can go to 3 and 3 to 4. That's it. So this is a cycle. This is not a spanning tree. This is a spanning tree. So we can construct many spanning tree out of this one, which is 1, 2, 3, 4. This is also a spanning tree. Okay. So the cycle, whichever tree or graph contains cycle, tree never contains cycle. Okay. Whichever graph contains cycle, that can never be a spanning tree. So this subgraph is also a spanning tree which contains all the nodes and exactly n minus 1 edges such that there is no cycle. Now 1, 2, 3, 4. This is also a spanning tree. 1, 2, 3, 4. And this is also a spanning tree. Like you can construct many spanning tree like this, right? But how many spanning tree are possible? Spanning trees are not unique, obviously, we have seen. How many spanning trees are possible here? So there is a formula for that, which is called that number of spanning tree for a complete graph is equal to n to the power n minus 2. Okay. For a complete graph only, we can calculate. We can give a formula for a complete graph only where we have all the edges. If we don't have all the edges, we cannot give the formula here. Number of spanning tree, number of possible spanning tree for a complete graph is n, where n equal to number of vertices. Okay, for a complete graph only, you can give a formula. It can be represented as kn because it have n number of nodes. This complete graph can be represented like this. So what is minimum cost spanning tree? Minimum cost spanning tree. It is called MST. Right? A spanning tree, if we represent each edge contains some weight, a spanning tree which have minimum weight is called minimum cost spanning tree. For example, let me construct a tree for you. First, you are given with a graph 3, 4. Here we have 30, 30, 10, 40, 50, 60. So now we can have many spanning trees, right? How many spanning tree can we have? This is a complete graph, right? So we can have 4 to the power 2, which is 16 possible spanning tree can we have. Out of those 16, which one is minimum cost spanning tree? So let me construct 2 or 3 tree. So you can calculate the cost, and you can say that okay, that is the minimum cost spanning tree. For example, if I construct something like 1, 2, 3, so there are algorithm for that. First one is Kruskal and second one is Prim's algorithm. So we are going to look into those algorithms and define some results out of those also. So this is 10, then we have 30, 30, 30, 30. So this is the minimum cost spanning tree. Its cost is actually 70. If you add all these up, it is 70. So you can never build a spanning tree by using some brute force or some intuition. I build this tree right now. So if you build another tree, something like 1, 2, 3, and 4. So this is 40 with 30. This is 30. The total cost here is what? 100. 40 plus 30 plus 30, which is 100, which is greater than 70. So this is a minimum spanning tree. Now, here you are given with a very simple graph, only 4 nodes. For example, if you are given with a graph containing 100 nodes, and you need to write a code or algorithm for that, okay, 100 node or 1000 node, you cannot simply look at the graph of 1000 node and tell, okay, that is the minimum spanning tree. So you must have some algorithm, right? So the first algorithm is Kruskal algorithm. Kruskal algo. This is a very simple algorithm. It says that, okay, only pick minimum node. That's it. And try to insert that into the tree, okay, so that the tree can grow. And we will never consider a node, a edge such that it make a cycle. Okay, for example, let me construct a tree for you. With example, it will be clear, okay? A, B, C, D, and E. So we have 70 here, 20 here, 40 here, 10 here, 60 here, 50 on this node, and 30 on this node. Okay, let's try to construct a minimum spanning tree out of this. First, we draw all the nodes, because in spanning tree we have all the nodes already. We know that we cannot drop a node. What is the minimum edge? It is 10. So we delete 10 We insert it here. It didn't make any cycle, right? It didn't make any cycle. So we can insert 10. Then what is the minimum edge? 20. So we insert 20 here. Whenever you are going for minimum value, you are going to use at the back of the mind, remember that you are always going to use min heap. Whenever you are going for the maximum value, you will use max heap. Okay. So first, using this value on the edges, we construct a min heap and we delete the minimum value from the top each time, right? So again, what is the next minimum? 30. So we insert 30 here. What is the next minimum? 40. So we delete 40. Now, can we insert a 40? No, we cannot insert 40 here. It will make a cycle. So you cannot insert 40. You just drop the 40 out of the equation. Now, what is the next minimum? It's 50. So let's delete 50 and try to insert it here. 50. Now you can see it's again making a cycle. So you cannot insert 50 also. It made a cycle. What is the next minimum? 60. So let's insert 60. So once you insert 60 here, it will again make a cycle. So you cannot insert 60 also. Okay. Because spanning tree don't contain cycles. Now only 70 is remaining. Once you delete 70, the weight is 70 here. You can put it here. And this is your minimum spanning tree. You can try to construct another minimum spanning tree. It won't be possible for you. Okay. There is no other minimum spanning tree for this given graph. There is no cycle, and we have how many edges do we have? 1, 2, 3, and 4. 4 edges. How many nodes do we have? 5. So we have 5 minus 1 edges in a spanning tree. We know that we have exactly 4, and the cost is also minimum. So how much is the cost? 100 and 130. 130 is the cost. So you can never build a spanning tree, minimum spanning tree having cost less than 130. Okay, you can try to build it. Now let's see what is the time complexity. Here you have E number of nodes, E number of nodes, E number of edges, sorry. E number of edges you have. So E equal to number of edges. So you will build a min heap, right? Once you build a min heap, number of edges, it will take order of E to build heap, build min heap. Min heap. Order of E will be or cost. Now you will do the deletion operation at max of E times. Each deletion will take, each deletion for minimum, current minimum edges, current minimum edge will take log E, okay, log E. And you will do it how many times? E number of times. So it will take order of E log E, okay, order of E log E. Right? So it will be E plus E log E, which is equal to order of E log E. So you can write it like E log E, or you have seen that log of E is equal to order of log V. So you can write it like E log E or E log V. We have already seen that relation, right? So it's order of E log E or E log V. So this is the time complexity for Kruskal algorithm. See, I am trying to construct time complexity for each algorithm which I am explaining. So using min heap, that's why min heap was very important, because wherever we need minimum element at any step, we are using min heap. So it's a very, like, you can say, integral part of algorithm subject. If you don't understand mini, go back and try to understand that. Try to see more example over the internet and understand that first. Then come back to optimal merge pattern algorithm or Hoffman encoding algorithm or job sequencing, or you can say knapsack algorithm, where we can take fractional like item, or this algorithm, so minimum spanning tree algorithm. Okay, so that's it for this lecture. We will see you. I will see you in next lecture. Okay, thank you all for joining.